Only 6 months into its Mercury orbit, the tiny messenger spacecraft has shown scientists that Mercury doesn't conform to theory. Its surface material composition differs from the other terrestrial planets and expectations prior to the messenger mission. Its magnetic field is unlike any other in the solar system, and there are huge expanses of volcanic plains surrounding the north polar region of the planet and covering more than 6% of Mercury's surface. These findings and other surprises are revealed in 7 papers in a special section of the September 30, 2011 issue of Science. Measurements of Mercury's surface by Messenger's X-ray and gamma-ray spectrometers reveal substantially higher abundances of sulfur and potassium than previously predicted. Both elements vaporize at relatively low temperatures, and their abundances thus rule out several popular scenarios in which Mercury experienced extreme high-temperature events early in its history. It seems that theorists will have to go back to the drawing board on Mercury's formation. Messenger has confirmed that Mercury has volcanic deposits on its surface. New data from orbit show a huge expanse of volcanic plains surrounding the north polar region of Mercury. These continuous smooth plains cover more than 6% of the total surface of Mercury. The deposits appear typical of flood lavas like those found in the few million-year-old Columbia River basalt group on Earth. Those on Mercury appear to have poured out from long linear vents and covered the surrounding areas, flooding them to great depths and burying their source vents. Messenger revealed an unexpected class of landform on Mercury and suggests that a previously unrecognized geological process is responsible for its formation. The science team calls them hollows to distinguish them from other types of pits that are found on Mercury. Images showed that the floors and central mountain peaks of some impact craters are very bright and have a blue color relative to other areas of Mercury. Hollows have been found over a wide range of latitudes and longitudes, suggesting they are fairly common across Mercury. Analysis of the images and estimates of growth indicate that they are relatively young and may be forming today. Earth, Mercury, Jupiter, Saturn, Uranus, and Neptune all have intrinsic magnetic fields, but Messenger found that Mercury's weak field is different. The distribution of energetic electrons in Mercury's magnetosphere is not consistent with what is known as Van Allen radiation belts. Mercury's magnetic equator is also well to the north of the planet's geographic equator. The best-fitting internal dipole magnetic field is located about 480 kilometers, or 298 miles, northward of the planet's center. The team found that sodium is the most important plasma ion contributed by the planet to the magnetosphere. Charged sodium particles are concentrated near Mercury's polar regions, where they are likely liberated by solar wind ion sputtering, effectively knocking sodium atoms off Mercury's surface. The formation process of these ions is comparable to how auroras are formed in the Earth's atmosphere. Messenger also detected helium ions throughout the entire volume of Mercury's magnetosphere. Researchers surmise that helium was delivered from the Sun by the solar wind, implanted on the surface of Mercury, and then fanned out in all directions. Mercury's weak magnetosphere provides very little protection of the planet from the solar wind. The conventional wisdom was that Mercury was just like the Moon. Messenger is showing scientists that Mercury is radically different from the Moon in just about every way we can measure. It is not the planet currently described in the textbooks. The Carnegie Institution has had over 100 years of extraordinary discoveries. To continue this tradition, Carnegie scientists need your support. For more information about this and other cool science, visit our website at carnegiescience.edu. This is John Strom.